All right, so in this video, we're going to go over bitwise operations, which are, you could summarize them as getting and setting values in sub-byte values. So what that actually means and why that matters is we can only read 1 byte at a minimum from some kind of source. We can only really address 1 byte, right? So let's say we have in our memory, we have some position, right? We can't ever point to just a bit or 2 bits inside of some structure. We always have to address things by byte. That is effectively what a pointer is. It's just an address to, it's a number that refers to some kind of position in a series of bytes, right? So we can never actually talk about bits from, let's say, a high level perspective. The way we actually deal with this and the way we actually have to do this is we have to use bit shifting, bitwise operations in order to get these values. And so we're going to go over shift left, shift right, bitwise and bitwise or. There are other things that you can also look into, bitwise XOR and so on, bitwise not and, but we're not going to go over those. The most common tool set that you're going to be using is bitwise or, bitwise and, shift left and shift right, right? So we're going to go over where you would use these, how you would use these, and so on. So you're prepared to look at data like this and look at a file format specification, for example. We're going to take a brief look at that at the end and actually say, hey, I can get values from this. This is not a challenge, right? So let's start with shifting right. So we have this X here, and I have set this up to print basically what X is on the right side. We're just going to add new values here, and we're going to print those as well the same way. And then we're going to see sort of, you know, what is happening here, right? What is happening to the value when we do certain things, right? So we have X2, which we're going to say is X shifted 2 positions. And we're going to see how that sort of changes our value here, right? Actually, let's start with 1. We're just going to look at 1 first, and then we're going to move from there. So let's say here we have our X2. And now we can see that suddenly we have 51. And that doesn't necessarily mean so much to me, but let's look at the actual bit pattern of these, right? So if we look at this here, we can look at this. I'm just going to add this here so we can see this very clearly, right? We have now moved every bit 1 step to the right, right? And importantly, if we were to say, raise this 1 here, we are going to be effectively losing bits. So let's just sort of do this for now. So we have this, right? Now I'm going to raise this to 2, and we're going to see what that outputs. And we're going to put our underscore here again. Now you can see we are effectively losing bits, right? We are now falling off the end here. This is important, right? There's nothing that says this rotates or anything interesting like this. We are shifting out bits. And this is important because tons and tons of code relies on this behavior. In fact, I would argue this is basically the only correct behavior you can have, right? Rotating or otherwise doing something interesting like this. This should be its own separate operation, right? This has no guarantee that you're preserving any kind of data or anything. We are simply modifying bits in a value, right? And so when we shift right, we are basically saying, you know, move everything to the right, right? Twice. So this bit here is going to disappear. It will move first here, and then it will just move off the end. It doesn't exist anymore. The reason we might want to do this is, let's say I wanted the upper 4 bits of this value, right? And we know that that's 0x6, right? And so that's going to be, that's just 6, right? And we want the upper 4 bits. Let's say we had a byte here that actually stored 2 values, right? And so we're going to treat that as, you know, that, and we're going to say, hey, if I want the upper 4 bits, right, I can actually just say shift right 4, right? Now we will see we got the value 6. We have extracted this value, right? And so now suddenly we can treat this x as storing 2 different values, and we can get them both at the same time. But of course, let's say we wanted these lower 4 bits, right? Now currently we have a value that also has these upper 4 bits set, right? So what we're going to do in order to get the lower 4 bits is we're going to mask this value. We're going to do what's known as an AND mask. So x3 is going to be x and 0x0f. And so what this actually does is it says for all of the bits here, we're going to make a comparison to this mask here. And we're going to keep the values where both bits are set. So let's illustrate this. First, let's show the actual result of this so we can be confident that I haven't done something crazy. x3 is 6, right? And I have done no shifting here. We got the value 6 only because of masking, right? And so let's kind of illustrate what that actually means, right? So I'm going to print the bits for, let's see here. Yeah, let's just do this. Mask is equal to 0, 0f. Mask, like this. Our mask is 15. And so 0x, 0f, right? You can see here that this now has a pattern here, right? All of the lower 4 bits are set, right? And so this value here, when we AND with this value, let's see here if I can put that here. What it's going to do, this operation, is it's going to keep all of the bits where they are set in both values. So we started out with this value here, right? And we ANDed with this, right? And so what that actually means is we're going to go bit by bit. That's why it's bitwise, right? Bitwise, we're going to say keep the bit set in the result if both bits are set, right? And so we're going to get 0 here because we have 0 in the original. We have 1 in the mask. That's not both, right? And we have, let me just sort of do this actually. Let's start from the left so we can write this out. Here we have 0 in the original, 0 in this. We're going to say 0, right? We have 1 in the original, but we have 0 in our mask. Likewise for the next one. Likewise for the next one, right? Because remember, we never set those bits. We have 0x, 0f. And then here we have 0 in the original, so we're going to get 0 in our result. We have 1 in the mask. Here we have 1 in both. Okay, that's a 1. We have 1 in both here. That's a 1. And then we have 0 in the original, 1 in the mask. Right? So this AND operation here, right, allows us to basically extract the set values in a certain area of a byte. Right? So that's this AND here. When we shift right, we're only just sort of repositioning. So that's a very easy way to say, hey, take the 4 upper bits here, right, and just sort of shift them right, and so on. Sometimes we have to combine these, right? So let's say for the purposes of this example, I wanted these 2 bits, right? So I want the upper, only these bits, nothing else, right? Importantly, I don't want this value here, right? I'm going to copy this and say this is our new interesting x, right? New x, like this, right? And we're going to set this so we can't actually kind of We can't do this improperly, right? I have this value here. If I were to shift right 4, or let's say we want these, right? These bits. That's not going to be appropriate, right? So shifted, or let's say upper bits, upper 2 bits, right? New X, and then we can shift a certain amount of positions, right? So here we would shift 5 in order to basically get down to this, right? So let's say 5 here, right? And we're going to printf, we're going to say upper 2 bits, and we're going to print this exactly like the other ones. No interesting stuff there. When I show the result here, you can see shifting is not enough, right? So at some point here, I'm going to have to do both of these operations. We're going to have to be more specific, right? So we could say new X here, right? And then we could AND with that, or we could AND and then new shift, right? So let's say we want to AND these 2 bits here, right, are 6. So here I can AND with 0x60, presumably, and then we shift 5. Let's see if we get the correct result here. Right? And we do. These specific bits are 3, right? Because we have 1 plus 2. So now we have extracted that value, but with a combination of AND and shift. I've first masked them out, right? So importantly, let's show the mask again, right? The masking was this, right? So the process here is going to be 0b 0, 1, 1, 0, right? And then 0, 0, 0, because we know in our mask we have zeros, right? And this works no matter what the value might be here. Let's say we have a 0 here, right? Yes, then we're going to get the value 2, because this bit here, these are the 2 bits we're interested in. They have the value 2, right? So this is a very reliable way to just extract 2 specific bits here. Oh, what value is that, right? This is often used for version numbers, Boolean values that they only require 1 bit, right? So we can have 1 byte represent 8 Boolean values if we so choose, right? And so on. So this and shift, these are the core kind of parts of extracting values from bytes, right? From 1 byte, for example, right? Or saying, hey, this is actually 4 bytes, but they actually represent 4 different values, for example. We can shift that, right? We can shift away an entire byte if we so choose, right? And so those are the core parts of actually extracting values. What about setting values, right? So let's say I start out with, we're going to just kind of copy this again, actually. New X again, like this. And we're going to say, these are now 0, the 2 bits that I was interested in, right? If we want to set values, right, we can actually, with upper 2 bits set, well, that's a long name. Here we can actually say new X again, and then we can OR, right? And OR is going to do a similar operation to our AND, right? So we're going to say 0x60 here. And again, these are the same bits, right? The same bit pattern as this one here, right? That's a 6 here. And so the result here is going to be let's do this for all of these. The result is going to be 230. Let's see here. Yeah, is this let me just print new X actually, because we should be getting the same thing, of course. New X. Yeah, 230. I can't read, honestly, binary that fast to know that that's 230. So now we're getting the same value as new x was, which was our goal, right? We wanted to set these bits in this value here, right? And so the actual operation that's happening here, right? Let's do this thing again where we sort of take a look at what this actual operation is, right? So we have a bit mask. That bit mask is this, like this, right? And here we have the result. This is an OR. So think like our AND, except if any of the bits are set, we're gonna set a 1, right? So here we can see 1 is set, here is not set, right? That means we have 1. Here we can see 0 here, but we have 1s here, right? And then we get 1, 1, right? Here, neither of them are set, right? We're gonna get 0. Neither are set here, so we're gonna get 0. 1 is set in the first one, so we're gonna get 1. 1 is set in the first one as well here, right? We're gonna get 1, and here 0 is set. The effect here is that we are now taking a value where these bits might not be set, and we're just setting them, right? Importantly, if they were already set, nothing is going to happen, right? So this is effectively like saying, set these bits no matter what, right? And so that's an OR. That's how you set a value inside of a bigger value, let's say, right? And shifting doesn't necessarily come into this, right? We're just saying, take this bit pattern, right? The original bit pattern, set these bits inside of that pattern. So the only trick here is to come up with the value that we want to set. And that's where coming, you know, knowing this, the structure of a byte, for example, that's where that comes in, right? But at the core of it, this is just saying, hey, I need to just figure out the value I want to set, right? If you have a multi-byte value, you can also set this, right? So importantly, we could just say, hey, you know, this could be multiple bytes here, 2f, etc., 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 right? There's nothing stopping us from doing that. We're just working with sort of bytes right now, and that's fine. And so this is how you set a value to any number of bits inside of a byte, right? And again, we're talking about bytes here mostly because when we're dealing with, you know, values bigger than bytes, right? And we don't need to talk about the specific bits and so on. Really, we have ways of doing that. It's not really a problem, right? But we absolutely cannot actually address bits, right? And that's where all of these bitwise operations come in, right? So to recap, right? When we want to get values and extract values in general from a byte, right? We have two main tools, right? We have shifting, which takes our value and our bits and shifts them in some direction. We can shift left, we can shift right, right? And so we can shift here a value by 4, which gives us here this, right? When we shift this, we shifted 4 positions. We're actually taking the upper 4 bits of this value. This is a common pattern, right? We're storing 2 values inside of 1 byte, right? This gives us basically, hey, we can say extract these upper 4 bits. That's a shift 4, right? If we want to only take out the lower 4 bits, right, of some value, we can say AND. We can say 0x, 0f, for example, right? Right? And so that gives us this AND pattern that says, hey, compare bits in these 2 values and keep the ones where both are set. This gives us an extraction of a zone, let's say, in this byte, right? We can then combine these also, right? In order to say, hey, I want to mask out these particular bits and then shift them right to get the value, right? And we can do this here by saying, hey, take this value. We're going to look for these 2 bits, right? These middle 2 bits inside of this upper 4-bit value, right? We can do this by saying AND first, right? Which means, hey, take out the 2 bits here, right? By masking out them, everything else is set to 0. This gives us this value here, right? And then we shift it, right? So we can then shift that 5 positions, which gives us in the end this, right? And bam, we have those 2 values. Now we know we can extract those. This is a numeric value now. We have extracted from this bigger value, right? If we want to set bits inside of a value, we use OR, right? So OR is basically going to compare bitwise here and say whenever we have a 1 in either of these, it's going to be set. This allows us to basically say, I want this pattern here to be set, right? So with the same bit pattern 0x60, right? We had this, right? Which gave us basically, oh, there's a 1 here, but a 0 here gives us 1 still. 0, 1 gives us 1. 0, 1 gives us 1. 0, 0 gives us 0 because neither are set, right? Likewise here. And then we have this 1, 0 gives us 1. 1, 0 gives us 1, etc., etc. The effect is we have set these 2 bits inside of the original value, right? And so that's how we can set these in a new, in a value, right? And get a new value out of it and say, hey, this is that value, but with these bits set, bam. And so let's take a brief look at sort of how this works in order to get some bigger value, right? And so I'm going to take a look here at LZ for frames. And you can see how we have a frame descriptor here for LZ4 frames. LZ4 is a compression format, by the way. We have this flag byte. And here we can actually see this kind of pattern with multiple Boolean values being inside of a bigger byte value, right? So first of all, we have two version bits, right? And we can see here, and we know from what we saw, because this is at the top here, we can actually just shift this. So if you shift this 6 positions, right? These upper 2 bits, right? We're gonna get the version number, right? We can also see here block independence is a Boolean. Block checksums are a Boolean value. The size being present is a Boolean value. The checksum of content is a Boolean value, like does it exist? And then we have a reserved bit here that is not used. And then we have whether dictionary IDs are present in this, right? So this flag byte here is used to set a bunch of Boolean values, right? And then we actually have this BD byte here, which is just sort of block descriptor byte. And this basically uses only 3 bits out of everything, right? And here it says, hey, the max size can be calculated based on this. We're going to primarily just take a look at this flag byte here, how this actually looks, right? So let's go to LZ frames here. And there's going to be code here that has no relation to what we're, looking at now. But the important part is here, right? We're pulling out the flags byte here. We're saying the current position in our data, pull out that byte, right? That specific byte, right? And then, so we can see here, this is a byte, by the way. And then we're going to take the version and we're going to shift it 6, right? So importantly, right, we saw here the 8th and 7th position, because remember, we're 0 indexed here, are the version, right? When we shift that 6, we're actually going down to, let's say we had this value here, right? 0B 1 1 0 0 1 0 0 0. Let's see. Yeah, like this. When we shift this 6, right? We're actually just saying, hey, move these 2 values down here. This is going to be just zeroed out, right? And so here we're going to get this, and we're going to get this. Like this, right? When we shift down. So we have that value. The version is just this, right? Block independence. we can see here, block independence here lives in basically let's see. Yeah, this is the second bit, right? In the upper 4. These are the upper 4 here, right? So block independence is going to be there, right? And we can see this here. We're taking the flags and we're saying and this, right? With the second bit of the upper 4 bits, right? 0x2, 0, right? If that's not 0, it means we have block independence. Now we have turned this into a Boolean value, right? So this basically turns it into a Boolean value here. Has block checksum, same thing, except we're saying the first, right? The first bit in the upper 4, right? And then it just sort of keeps going on like that, right? This is how we can address these, right? Do we have a content size, right? These are the lower 4 bits. This is the upper bit of that, right? That's 8. So just take 0x08, compare it to 0, right? And then the dictionary ID is the lowest one. That's the first bit, right? And bam, we have these now. We have extracted these, right? So extraction is just shifting, basically shifting right, mostly, right? And ANDing, right? Bitwise AND. So I hope this was useful. And if you like this content, if you like the sort of more fundamental content, or if you don't like it and you want more interesting, let's say, content, we're going to be using some of these things, and I'm going to try to, talk about LZ4 in depth, right? And so on. So we're going to be using these fundamental things that we have learned, and so on, to explore that and see what we can do with Odin, and so on. If you like this type of content, if you think it's useful, and so on, feel free to drop a comment, like the video, subscribe, and so on. It helps a lot, especially with motivation. Okay, have a nice day and ciao.